Hello to all the subscribers of the Global Energy Association. Our today's guest is Yi Chu, Director of Precourt Institute of Energy, Professor of Material Science and Engineering at Stanford University. Dr. Chu was nominated for the Global Energy Prize for exceptional contributions in nanomaterials design, particularly for transformational innovations in battery science and technology. Material studies have significantly varied the energy storage sphere in terms of using various kinds of materials and their combinations. Moreover, we already use different types of batteries in various spheres of our life. For example, we have lithium-ion and lithium polymer accumulators in our cell phones, lithium titanate ones in electric cars, and so on. So what, in your opinion, will be the battery of the future?
Yeah, a battery is, of course, a very, very important, Sophia. So I'm glad you asked these questions. We have seen currently lithium-ion batteries are dominating for consumer electronics and for electrical transportation. I think lithium-based system will continue to dominating in the electrical transportation for the ground transportation case. However, then we ask the questions, what about how could you increase energy much higher, double the current energy the batteries can store, even it's based on lithium ion? That's what I've been working on in the past more than 10 years now, is to utilize new materials using nanotechnology to nearly double the energy density of the current lithium ion batteries. And then certainly batteries can also be used for grid-scale energy storage, for integrating solar and wind electricity into the grid. For this application, it's not clear lithium-based batteries will be the answer. It might be, it might not be. It could have other battery systems also working, maybe much better than the lithium ion. I also have been working on this area for the past 10 years also, coming up new batteries chemistry that could do the grid-scale energy storage with much lower cost, much longer lifetime.
So please tell us more about how did you manage to reinvent the battery field by enabling new materials with 10 times higher charge storage capacity?
Yeah, coming back to lithium-ion batteries, in order to store energy, you need to store charges. You need to store lithiums. Graphite is used in existing lithium-ion battery as anode. That's the negative electrodes. Lithium cobalt oxide, so-called MMC cathode, lithium iron phosphate, they are using it as the cathode. In order to store a lot more energies, you need to store a lot more charges, that's lithium ions and electrons. So new materials to replace graphite, such as silicon, it can store 10 times more charges compared to the graphite carbon as the anode. If you replace graphite as anode, you increase on the anode side 10 times more charges per unit weight. Certainly, you also need to store on the cathode side. If you can do 10 times more charges, such as using sulfur as the cathode, then you can increase the energy density of the batteries by a lot. But you still need to consider the voltage. Make sure its voltage is high enough. So at the end, for example, using silicon, using metallic lithium anode, using sulfur cathode, you can double 3 times or more of the energy density of the current lithium-ion batteries. That's how new materials can help, and how using nanotechnology to overcome some of the material science issues in order to make those new materials to work is so powerful.
Talking about lithium, have you felt any consequences of a recent political upheaval in Bolivia, which is the main producer of this metal?
Certainly, well, lithium is a concern. Indeed, for example, cobalt is a concern as well. There's a price concern, there's a geopolitical concern. lithium distributed in a limited number of countries. And well, people just need to really need to work out this, how to collaborate to have lithium available to push for the clean energy revolution to fight against climate change. And lithium source, and people also need to look into non-traditional lithium source. Indeed, in so many countries, there is a salty lake, there's underground, water that contain lithium. Maybe lithium concentration is not as high as some of the traditional sources, but there's a lot of lithium available around the world. At the end, ocean has infinite amount of lithium. It's just concentration is a little low. Indeed, in the past 5 years, also my lab has been working on extracting lithium from ocean. We invented new technology for doing that. It's looking promising.
Oh, that's very interesting. But there is another concern. We know, for example, that production of graphene, for instance, may not always be considered eco-friendly, not to mention the disposal problem of accumulators in general. In this regard, how much better is design using a stainless steel and not covered with silicon nanowires, for example?
Yeah. If I understand your question right, it's the whole thing of a circular economy, from production of the battery usage, second use, and recycling, and back to reuse. I mean, these got to be within the whole cycle. Everybody now need to concern about this. For the energy industry, the scale is so big. It makes a lot of sense. It's completely necessary to consider the circular economy problem.
Okay, how efficient may the future accumulators become? Or will we be able, for example, to send small boxes like, modern power banks containing hundreds of megawatts or even gigawatts of energy to remote regions of Africa, Alaska, or so on?
Yeah, that's very interesting, Sophia. So for the battery technology, we kind of know it's a fundamental limit already. What's the best chemistry available based on electrochemical reaction, based on the chemical reaction, right? We are probably theoretically could expect the energy density per unit weight, theoretically, right? This is about only 10 times of the existing lithium ion. That's it, that's about it, about 10 times only. And those chemistry very hard to work out. I would say if we can double or 3 times, I mean, the whole electrical transportation, electrical car, including the truck, is already there. For electrical flight, we will need more. We'll probably need about 4 times to 6 times of the current technology in order to do inside continental airplane. Cross-continent airplane require even more. Then you say, well, if I want to have a small box to deliver huge amount of the energy, that is 100 times of the current battery technology. I haven't seen any battery chemistry can do that yet, right? So then you say there got to be a nuclear batteries, maybe possible, certainly not from the electrochemical system.
But future is unpredictable. I hope one day maybe we will see such a technology, such a powerful technology.
Yeah, I'm excited about that. So if that technology somebody could invent, so I will be thrilled to see that.
I also know that Stanford University have invented this self-healing battery. What is it?
Yeah, this is the work myself and my colleague, Professor Zhenan Bao in chemical engineering, we collaborated together to put in a self-healing polymer. This polymer chain in room temperature, they can move around. They form hydrogen bonding. If you break it, hydrogen bonding is reversible. It can reform. So once it reforms, the breaking part get healed. So And use that for the batteries, right? Because battery, once you put in a lot of lithium, you charge during charging, discharging, this volume expansion create cracking and so on. If this cracking happening, batteries could die. But now with this polymer right there, the polymer chain move around and find each other and then heal. Now the battery can be reused. So it's really, really exciting. You know, just like human body, right? Human body has the function of healing. If this device have healing function, that could be very, very exciting for very long lasting batteries.
All good examples we take from the nature, like for example, artificial leaves of this self-healing battery, right? But does this polymer, it needs some exact temperature, right?
Yeah, that's why one human coming in to engineer the polymer chains, this could be very exciting. So you can engineer this polymer working at room temperature. Engineer is this very dynamic polymer chain movement temperature measure. It can be doing the healing function across in many temperature range.
Oh, this is really exciting. Thank you, sir, for this short interview to all our subscribers. It is one of the series of chats. There's nominees for the Global Energy Prize. I wish you all the good luck in this process, sir. Thank you very much once again.
Yeah, thank you, Sophia.